Recording this computer. So, hello everyone, and welcome to the second meeting of this AI reading group that we are going through. And as the last meeting we had 2 weeks ago, the last get together we had was about the introduction. It was about the the environment where we are in, how foundational models came to be, what to expect from them, and what our company is expecting, how to drive value out of it. And on this chapter, we're going a little bit more into the technical aspects of foundational models. This one specific. Oh, I should have added the title of this chapter, but the title is developing foundational models. So a little bit more about the algorithm. As we discussed before, since we don't have enough, not everyone has access to the book, which is AI Engineering by Chip Huyen. I will present and then we can discuss a little bit later. This is, if you want to stop me at any point in time. Did anybody go through the book or not yet?
So I'm in the middle of chapter 2.
Yeah, it's a long chapter.
Same.
Okay. Yeah, I gotta be honest that I started reading yesterday, and I underestimated how long that chapter was and how heavy it was. It was difficult to read it. So the TLDR of this is what is a foundational model in terms of a technical definition, how it is created, how do you develop some of the algorithms, some of the architecture, but most importantly, how to make it usable, because I'll go a little bit of it. It's just the output of the machine learning part in itself creates issues, and then we have to deal with these issues to make something useful. And for me, this is the core of the chapter. This is an image towards the end of the chapter. Don't worry, I will go through the different pieces in this. But basically, this is your input. And you want to have the final model. And this is low quality data. And everything here is about how to deal with the low quality data that you have over here. So starting on the left, this is where we want to get. It's the final model. This would be like the GPT or the Mistral. They are over here. And over here is the start. So these are models, they are next token prediction. So you have a phrase and you want to predict the next word based on context and the model itself. But for you to get a significant results in terms of generating, you need tons and tons of data. If you want to increase at the machine learning level, if you want to give a linear increase to the model, like a 1 or 2% increase, that will require way more data, way more resources than the previous 1 to 2%. So if you go to 80 to 85 is one cost, 85 to 90 will be 5-10 times that cost. And that grows exponentially. Since we need so much data, we use all the data we can. Like basically, they scrape the entirety of the internet and feed into the model, and everything that comes with it. Not everything on the internet is good, as we have learned in the past few years. There's a lot of questionable content in there that ends up in the model and that the model learns from. We used to say on machine learning that this garbage in and garbage out. If you feed the machine learning training algorithm garbage, the answers will be garbage as well. But there's also a lot of useful stuff on the internet. So now the problem is, how do we ungarbage this garbage that we're generating? And that's the entire right part of the algorithm of the graph. So this is self-supervised pre-training, which means we generated a lot of phrases and the next token, phrases, next tokens, phrases, next token. So that's how it's trained to predict the next token. And then the second step is this. We trained on a lot of low quality data because high quality data is very expensive. Getting good, getting low quality data is just creating a script that will parse everything and create it. But creating high quality data means auditing and validating that data, and that's expensive. So we have a lot less. So what we can do is, from the model that we created before, fine-tune it with high quality data. Fine-tuning means taking that model, taking the high quality data that is generated through humans. So there's some human interaction there to get this data, to vet this data, to compare. You can use things like Amazon, I think, Mechanical Turkey, and other tools like that to label images, label text, and give better answers. And use that for fine tuning, which means after you pre-train, you train a little bit less with high quality data so that the answers get better. But note that there's still garbage. Like, you have improved a little bit, but there'll still be a lot of garbage in the middle. So it's like you had trash wine and you put some good wine on it, so it's less trash. And now it will work better with fine tuning, but still there might be issues that will come up. And then there's the right side of the graph, which is after you have fine-tuning, fine-tuned, you have a model, how do we make it even better? And that's where things get a little bit more complicated, because first there is what they call a reward model. You train a different machine learning model to identify what's trash and what's not trash. So you request 5, 6 different results from your fine-tuned model, and then use a reward model to try to identify what's the one with the most likely to be high quality. So this is over here, reward model. It doesn't always work, but it does a good job, but it also requires you to generate multiple times. So if you want to give the reward model some options on how to score, you're gonna have to keep generating a few different responses. There's also things that are related to a reward model, like conditional. So you can keep generating till, like, suppose you are doing code completion. You can keep generating until the test pass. But at some point, you might never, like, that's an infinite, that has a chance to be an infinite loop, right? Like, you generate, it fails, it fails, and it turns into like this cycle. At some point, you have to say, no, that's done. No, we cannot handle that. But that's another type of deciding, of improving the quality of the final model. And for this RLGF, this prompt is, okay, let's craft the responses that we want to provide, that the model to provide. Like, let's give really, really high quality examples for the model to learn on. Comparison data is, I generate a lot of different responses, and then I'll give to human labelers to tell me which one is better than what. And I will use that to train this rewarding model. So the reward model will have already some human input to decide what is good and what is not. And that's where we're gonna get our where we're gonna get our final model in that will offer the customers or the users. So now this final model, this is what we are using right now. This is our underlying like models that we use. But we could as well, for example, fine tuning. If we wanted to fine tune, then we would go back to this step and do it a little bit better on the next ones. Yeah, so, and as I mentioned, at least on this chapter, the summary is that most of the AI engineering is about ungarbaging the garbage that was added. So because we needed better results, we put an absurd amount of data for these models to train that are not quality data, and they pick in the responses every now and then. This is what causes hallucination because the model will predict something. Doesn't really mean that it's going to be correct, but it will predict something. So you need to avoid that. And then there's the question of alignment as well. So you don't want for example, you don't want Duo to be answering geopolitical questions, right? That's not the goal of Duo. Duo is about DevOps and development. So how do we avoid a general purpose model from going to that direction? The chapter also goes into the idea of not random, but diversification on the responses, because this is not deterministic, this is probability work. You can make it less probabilistic or more probabilistic, and that's the role of temperature, for example, top K and top P parameters. Temperature kind of normalizes the probability of the tokens. So every token one token doesn't have that much more likelihood to appear than others. So that's how temperature works. Top K just takes, instead of looking at all of the tokens, it just looks at the 50 more likely, for example, or the 100 or the 1,000 more likely to appear. Top P is some similar, but it's a cumulative distribution. So yeah, that is the chapter. That's at least what I understood from the chapter.
It's interesting. I don't fully understand, and I don't know whether you know, Eduardo, is that how does this the whole oral HF cycle work? Like, do they have to hire people to do this, right? Like they have to give them like
Yes.
tons of predictions and so do they use like Scale IO or one of these services? Like how do they do that?
So the chapter, I won't share the book in itself here because I don't know if we can share the book on this recording. Uh, I don't know all of those licenses thingies, but the book goes about this. Yes, OpenAI built a tool for this where they hire people to label into there, to label and rank responses. And they are expensive. Like they were doing some statistics. They showed some statistics for one of the RH LA or reinforced learning, like our LHF. They had like 90% having at least a master's degree or something because they have to provide facts, and it takes like half an hour for you to write a good response because you have to go and search and build that response. Even validating an output from the LLM takes like 3 to 5 minutes because you have to fact check, especially because it sounds convincing, like the LLM sounds very convincing. And fact checking that is what they say, like it takes an order of magnitude higher to sift through believable bullshit or something like that. So that kind of it's very, and then you have like metrics like inter ranking where you give many people, like you have 10 people and you have 100 cases that you want to rank. So you give 15 to each one, and some are repeated. and you use the repeated ones as a like balancing or a correction across them to see how like each ranker, because each ranker behaves differently as well. Even if you yourself, you might read an answer today, that's okay. You think it's okay, but you read the same answer tomorrow, and that's going to be a different one. So that's that adds a lot of noise into the into how this acts. But yeah, it's you can use it in Mechanical Turkey for this. That was a common thing for labeling data back then. But in this case, I think at least what the book suggests that OpenAI created their own tool for labeling.
Yeah, because I mean, you want the tool to feed back to your whatever data ingestion process so that you can
Yeah.
then go and
Mhm.
feed it back, right? Yeah, that makes a lot of sense. Now, I'm curious about the other models as well, the reward models, like you know, what kind of models those are that can decide, you know, how good. Like they also have to be like LLMs, right? Some sort of language NLP models
Yes.
as well.
Hmm.
Um, so
Yeah.
yeah, I mean, the reward models themselves have to be as good as the LLMs to decide, or at least pretty good, right? Enough to
Yeah, it needs to
understand.
be pretty good. The author argue there's some papers that say that they don't need to be as good because you are not generating, you're just judging. But I think that's for the average case, because we just feel like it's really good. It's really hard to go through believable trash. So with that appears correct, but it's not actually correct. And understanding those use cases, those specific scenarios is hard, even for a LLM. The next chapter is evaluation, which is a very interesting one that I'm happy is already available. So I think so far that's one of the most interesting. For this chapter, I really want to go through the Andre Karpati's tutorial on how to write a GPT, because I think it goes really well with this book, with this chapter. It really explains the algorithm, the attention mechanism, the reinforcement, the RNNs behind it. So I really want to go at some point through that chapter, through that presentation.
I tried his talk, but one of the things I noticed about that talk was that it was became dense pretty quickly after you reach like the 30% mark on
Mhm.
like I followed it up to there, and then it went into some math which I just didn't understand, and so
Yeah.
that's when I stopped.
Yeah, I think even this chapter we had already a lot of math that it was hard to pick up by someone that is not familiar with machine learning. A lot of different names, a lot of different probabilistic uh, like terms and things that it was difficult. So I'm gonna open the. I was going to open the agenda, but okay. I'm gonna stop sharing my screen.
I was watching a video on from Mistral, I believe, on the training of these models, and they spoke about how expensive it is at this whole data sanitization, etc., that they need to do. You know, they need to get it right the first time because it's so expensive. You know, it costs from 10 to hundreds of millions of dollars just to train the foundational model,
Yeah,
and so you know how important it is to get that data right before they can do it because they only get one chance to actually train,
yeah.
right? And that's a lot of pressure.
Paulo, you added some comments on the agenda. Would you like to go over them?
Yes, sure. So for the first one, it's just sorry, this is where I was taking notes and I didn't add it to the agenda. That was a mistake. But yeah, one thing. So I read 50% of the book, and I'm not sure if he talks about memorization. But one of the problems, it's even mentioned in the LLab top 10, but it's kind of like overfit where
Yeah.
if you narrow a lot the data that you give to a model, so you don't give it diversity enough, and the chapter talks about that, the model will start to replicate the data that it trained, and that can cause some complicated problems like copyright issues where the model is like just spitting out exactly what it read. And a specific example would be like writing code exactly as it read it, or repeating like secrets, tokens, etc., because it read it. And yeah, and I shared these well, it's a blog post on Hugging Face, but about how the some people measure the memorization on that model that is the star coder a while ago, and that is interesting. So I don't know if the chapter went over that, or if you know anything about like
The chapter
techniques to
didn't go through
mitigate
it
this.
yet. At least I don't think it did. Well, from what I read it, and it didn't. The first chapter it mentioned memorization as a problem. With some, I read some star coder had a 7% problem or something like that, or it was not small, it was not insignificant. But I think later on we're gonna see more of this. The copyright problem is pretty complicated. I was going to say something that I forgot. Okay. No, yeah, it's especially for us, if we are training on like on our repository data, which we don't, but if we decide eventually with user approval or some of the user approval to train, that can lead to problems.
Yeah. And I mean, you can still have these with external models, right?
Yeah.
I think you had now with the Figma where they said they weren't using their model, but it was still replicating the company's design.
Oh, that's nice. I'll click the link that you shared over here.
Yeah, so that second link, I crossed paths with this while reading chapter 1, in fact. But this is an interesting one. So not that I fully understood it, that's relevant, but it gave me a better idea of all the parameters and all the multiplications that are happening. And I think you can kind of see what does it mean to be like the attention part while following that. And it's cool also because it starts with like a nano GPT that is approachable. And if you see like the difference for the other GPTs, it's massive. It's like, and there's no GPT for the
that's what they say, it's exponential. Like if we want to go the same level, at the chapter mentioned that if we want to go for the same level of change that you went from GPT 2 to GPT 3, we will have a model with 100 trillion parameters. We would need that much. So it's
that's
pretty
impressive.
insane.
So I think that for okay, that might be wrong here, but I think that for that UI, the models are running on your browser. So I think they wouldn't fit GPT-4, like even if you want. Those are the models that fit
that's
in
interesting.
your browser.
That's a very
so
interesting
they are
link. I like
executed
this.
there.
That's a good one. Yeah, cool. Yeah, so we are out of time, but you look at just the difference between Nano and already the small GPT.
Nano is the one that you can understand.
That's what I was looking at. It's so different.
It's how you understand what a billion actually means. It's like it's not something the human brain has a terrible problem understanding the concept of a billion. It's just too large for the human mind, and this really showcases like the difference. Like okay, I need to scroll this much to even see that. Wait, shit. Here.
I showed another link
like
that is the 1 pixel wealth.
Yeah.
If you want to go into the, I don't know if you know it, but
yeah, exactly.
It's a good visualization of the difference between 1 billion and 1 million.
Is using rice as well. Using rice is a good. Okay, so yeah, we are towards the end of today's conversation. Thank you for joining. It was a very difficult chapter in terms of technical, especially if you don't come from machine learning, if you don't have experience with machine learning. There were a lot of concepts over there that became a little bit difficult, but yeah, it was a fun one. Thank you for joining, and I hope to see you next time. Bye.
Thank you.
Thank you.
Thank you for
Thank
organizing
you.
this.